In this video, we're going to learn about descriptive statistics. What can we calculate in order to numerically describe our data? We already looked at graphs and tables to give a visual of our data, but we can get more specificity with numerical summaries. So we're really going to be focusing on quantitative summaries, which include measures of center or central tendency, the spread, and we're also going to look at outliers. So we can think of measures of central tendency as being like looking at your typical value. So if you were to look at your distribution, what value do you think most typifies what is happening? So think in terms of, I don't know, your GPA, right? You think of your GPA as representing, if you convert it, representing basically what you often receive on assignments or on your report card, more often than not. Now, there's probably some values that are higher and some values that are lower. You're probably not getting exactly the same outcome on every single assignment. That would be amazing. But the GPA typifies what your overall performance is. So often when we're looking at a data set, so this is the number that we're looking at to just sum it all up. Okay, so there are two ways that we're going to talk about for measuring measures of central tendency, and you've seen these before, so that's always nice when that happens. So in this case, we're looking at median, looking at the middle, right? So if we want to calculate the median of a distribution, and let's say our distribution is right here, then we want to find the middle value. So what we normally do first is we'll organize them in some order that makes sense. So in this case, I'll just write them real quick. Negative 17.5 is the lowest, and then it goes to 2.8, 3.2, 13.9, 14.1, 25.3, and 45.8. Hopefully I didn't leave any out there. And so when we're looking for our median, once all our values are lined up, we're basically just taking the value in the center, and that would be our median. That would be the middle value. Okay, so it splits the distribution in half. So now there's a 50-50 chance that of a value being above or below the mean. Okay. We also sometimes call it, I don't know, when we talk about quartiles, it would be like your second quartile. Okay, but 50% of the data lies above and 50% lies below. All right, mean is slightly different. And again, you've calculated mean before. You probably recognize this formula for mean but you may not recognize this part. We actually do say y bar. Okay, the bar above a variable means take the mean. Okay, means average. Average and mean kind of go hand in hand. So that's what that bar represents. So it's saying find the average of some variable y, and you do that by adding up all of the numbers and dividing by how many there are. And again, this may be notation that some of you have seen and some of you haven't. This is just summation. Okay, so that E is basically saying sum up all of the y's and divide by the number of the y's. Okay, so again, mean isn't any different than what you've learned before, but no, mean is kind of like the balance point. So if you had a distribution and you cut it out of a piece of paper and you wanted to balance it on your finger, okay, that's where the mean is. The mean is where weight-wise this thing would balance on your finger. Okay, so depending on whether it's skewed, your balance point is going to move, okay, to where it will actually rest on your finger. So we also think about it's maybe the fair distribution of outcomes. So like let's say we had a lot of values and we wanted to think of like one typical value that I could evenly redistribute back out to people. It would be the mean. It's like the fair redistribution of outcomes. So let's say I was looking at incomes, and we know that incomes vary, but let's just say then I gathered everybody's information about their income and I wanted to fairly redistribute income so everyone got the same thing. That would be the mean. So if we have two measures of center, how do we know which measure we're supposed to use? Should we use the mean or the median? So there actually is a rule in statistics about how you make a choice about which one you use, and it has to do with whether your distribution is skewed or not. So if you have a symmetric distribution, you're going to choose to use the mean. And the reason to do that is we have many statistical tests that deal with mean, so it's going to make your life a little bit easier. But if your distribution is skewed, you're going to use the median. And let's just talk briefly about why that's the case. So let's just take a quick set of data, really simple. 2, 3, 5, 7, and 8. And let's think about the mean and the median. So if I was to take the average, the mean of these, I would get 5. I hope that you agree, okay, and you can test that out for yourself. And if I was to find the median, do you agree that I would also get 5? Okay, so in this case, my distribution happens to be symmetric. And mean equals median. All right, but let's just change this a little bit. Let's change our values a little bit. And let's, instead of an 8, let's say 100. Okay, so I don't know, you might call that value an outlier. You might think that there's something very unique and different about that. Does this adding 100, does that change the median? No, 5 is still the median of that distribution. But if you imagine adding all of these values up now and dividing by 5 to find the median, do you agree that the median is going to be significantly larger? Okay, so when I have these higher values, if I have a skew or towards one side, or I have some outliers, they're going to pull the mean towards it. Okay, so the mean is sensitive to skew. So I don't want to use that. I want to use something that's typical. So that's why when we have skewed data, we use the median. Okay, because median is not affected by outliers. Okay, but mean is affected by skew and outliers. So that creates some problems with the measurement. So if we take a look at some of these distributions here, I look at the overall, right? It's pretty sharp there, but then look, I've got all of these values up here. I've got this guy here, right? I've got this guy over here. So it's got outliers. It seems like it's skewed to the right. So in this case, we should use median. We don't want our mean to be affected by those values up there. And in this case, if I was to draw the overall shape, do you agree that it's pretty symmetric? So in this case, it's approximately symmetric. So we're going to use mean. So now that we've talked about measures of central tendency, let's talk about measures of spread. Now it might seem on first thought, since you probably haven't talked much about the variability or the spread, so this is sometimes considered variability in your data, you might think it's not as important of a value to think about as maybe center, since you've talked about measures of center since you were in elementary school with mean, median, and mode. But in fact, measure of spread is the reason why we have statistics in the first place. So when we gather information, we know that all values are about something, all values are not going to be the same. So it's that variability that makes prediction difficult. And a lot of statistics is trying to understand the world around us to hopefully, I don't know, navigate it differently, maybe make some predictions about what we think will happen. So really, spread is a very important measurement. So we have a few ways to measure spread. The first we'll talk about is the range. It's simply the maximum value minus the minimum value. So if we look at our example down here, our minimum value is negative 17.5 and our maximum value is 45.8. So to calculate range, we're simply going to take 45.8 and subtract negative 17.5 to find that the range of our data is 62.6. And usually we have some units or something that we would refer to in order to figure out what does that mean. But range is the maximum minus the minimum. Interquartile range is the range between quartiles. A quartile represents 25% of the data, 25% of the data values, right? So we remember median splits our data into two equal pieces, right? 50% are below, 50% are above. quartiles, instead of breaking into 50% segments, breaks it into 25% segments. So the interquartile range is the range of the middle 50% of our data. Okay, it's kind of really talking about what's going on close to our center. So in order to do that, we're going to figure out what the third quartile is. Okay, that's the 75th percentile, if you want to think of it that way. Okay, think like SAT scores, that kind of thing, minus Q1, which is the 25th percentile. So a percentile is simply telling you what percent of the values are below the number you're reporting. So the Q3, or the 75th percentile, means that 75% of all the values in your data set are less than whatever value you report for Q3. Okay, so let's take a look at how we could figure those out. So we've already determined that the median of our data is 13.9. So from there, if we take the lower 50% of our data and we find out what the, and there's two ways to do this. Sometimes people will include the median and sometimes they don't. It's strange, but statisticians don't necessarily agree. But in this case, we're just not going to include the median. We're going to take our lower 50% and we're going to look at the middle of our lower 50%. That's 2.8. That is Q1. Okay, and then we're going to take the upper 50% of our data and we're going to take the median of that, and that is Q3. So to calculate interquartile range, we take Q3 minus Q1, so 25.3 minus 2.8, and we find out that our interquartile range is 22.5. So we learned about the range and the interquartile range, and they're often used in conjunction with median. But there are more measures of spread, specifically the standard deviation, which is one that we use in conjunction with mean. Okay, so when we report mean, we're going to report the measure of spread using standard deviation. So this is the formula for standard deviation. Looks a little bit scary, and we're just going to briefly touch on what it's calculating. Standard deviation takes, so y represents a value in your data set. So, and remember, y bar represents your mean. So when you take y minus y bar, essentially you're finding that's the distance of a data point from the mean. Okay, and then they square that value. The reason we square is, remember, that's going to make, it will make all distances positive, and that will be important in a second, and for large different distances, it makes them stand out because it makes them larger. So think about a small distance might be 1. If I square 1, I just get 1. But if I have a distance of 5 and I square that, I get 25. So it makes those values that are further away from the mean stand out more. And then remember that this is summation. So this is the sum. So that adds the squared distances. So that's why it's important that one of the reasons we square to make all the distances positive, they don't cancel each other out then. So if we didn't square them, we'd have some distances that were negative, some distances that were positive, some like that means they were above or below the mean. And when you added them together, they would have just canceled each other out and you would have gotten 0. So that's one reason that we square. So the sum of all the distances, and then essentially when we divide by n minus 1, imagine, we're not going to talk much about why we have the -1 in this course, but if you imagine summing a bunch of things up and then dividing by n, that's kind of like taking an average. So it's like an average of the squared differences. Okay, and then finally, You square root all that information because remember you squared it in the first place. So you need to kind of get things back. So if you square feet, now you have feet squared. Well, I was talking about feet, so I want to go back. So we're going to square root to get back to feet. Okay, so it undoes the earlier square. Okay, so now that we've kind of talked through the formula, from now on, you're just going to use the formula, you're going to use some technology to help you calculate these. You're not going to have to plug values into this formula. It would take you forever. But it's kind of good to know what standard deviation is measuring. So standard deviation is measuring basically the average distance of a data point from the mean. And the way that it's calculated makes the values that are further from the mean stand out more. So as we discussed before, why do we care about spread? Well, we care about variables because they vary. We care about gathering this information because something about the information we're getting is mysterious to us. There's something about it that we can't quite predict. So we gather it and we analyze it in order to try to make sense of it, to make predictions. But it's just because those outcomes vary that we have statistics in the first place. It tells us the unknown. It points out that something's up. Why don't I always score exactly the same on every test? I don't know. What's up with that? Am I scoring wildly different? Am I sometimes scoring at 10% in a test and sometimes 100%? Well, that would be a large standard deviation, a lot of variation. Am I really scoring somewhere between 85 and 86 every time? Well, then there's very little variation. So that gives us a little bit more information about the kind of data that we're talking about. So there are just two other measures that we're going to talk about very, very briefly, and those are skewness and kurtosis. I just want to put those terms out there. You're not going to calculate them or use them, but just know that they exist. So we talked earlier about skewness and how looking at a distribution, whether it's skewed to the right or the left, helps you make the decision about using mean versus median. So all skewness measures is the asymmetry of a distribution. And the other one is kurtosis, which measures how peaked or flat a distribution is. So you might have a distribution that's like that, or you might have a distribution that's more like that. Okay, and so kurtosis is going to measure that. So negative would be flatter like this, and positive would be more peaked like that. But again, that's really all. I just want to plant those terms for you, but that's really all we're going to cover with skewness and kurtosis. So finally, let's talk a little bit about outliers. An outlier is a point that really does not fit with the rest of the distribution. So how do you know if a data point doesn't fit, and what do you do about it? There's lots and lots of different things. It totally depends on the context of the information. But what you want to think about in identifying an outlier, since an outlier is a data point that doesn't fit, so you're looking for values that are far away from all the other values in your data set. Okay, they're unusual. And the question you want to ask are they unusual because you had a measurement problem? Okay, that could be human error, like you just misread the number. That could be telling you that your measuring instrument is off, or something happened, or it malfunctioned. Okay, so it could be a measurement problem, or it could be a subject that is very atypical. And sometimes that's really interesting when you have a subject that's very atypical and you want to talk about that outlier a little bit. But sometimes an atypical subject is really not a valuable piece of information for the kind of study that you're doing. So you just want to be really thoughtful about your outliers and what you choose to do with them. And usually the suggestion is you often will conduct your analysis with the outlier and without, and you'll make sure you definitely talk about them.